So today we are going to start discussing integrality properties, which will be very important in the following. But first, a result that we will be exploiting once we have set up integrality. This result has to do with the isomorphism we have. With the isomorphism we have, and we have discussed several times, between the group algebra on one side and a direct sum of endomorphism rings, endomorphism algebras, which we may call V, let's say chi, okay? Well, V chi is an irreducible module, say an irreducible module for CG, for the group algebra, corresponding to the representation, an irreducible representation, to an irreducible representation. Rho from G to GLV chi, whose character is chi. Okay, so we use as a parameter the character. So chi ranges over all irreducible characters of G. Okay. So we had seen this isomorphism, and in particular we had seen that once you have so this is an isomorphism of algebras. Of C algebras. Well, okay. I usually say just algebras because I think all our algebras are over C, over the complex numbers. And this induces, as we have seen, this isomorphism induces an isomorphism of the centers of the two algebras. An isomorphism between, say, the centers of the two algebras. Okay, so and we had seen that the center of the group algebra is a subring, a subalgebra, is a vector space, say, with bases the sums of the conjugacy classes. Let us introduce a notation that will be useful later. So let's see be a conjugacy class of G, okay? So C will be of the form all the conjugates. Will be of the form G to the X, where X ranges over G. So this is the conjugacy class of the element G. And we denote with sigma of C, the sum of elements of C, of the elements of C. Taking each element being taken once, okay? So let's consider an example for clarity. So we have S3. S3 has three conjugacy classes. One is the class of the identity. One is the class of the elements of order 3. as usual, it's a symmetric group, so it's the shape, the type of permutation that determines its conjugacy class. So this is a class, let's say C naught. This is C, well, let's say C1. This is 3 because it's made of elements of order 3, and then you have the elements of order 2. Okay? And so the idea is that sum of C1 is simply 1, that the sum over C3 is simply 1, 2, 3 plus 1, 3, 2, and the sum of C2 is simply the sum of these 3 elements. Okay? So where C is a class, is a set, I mean, with the elements are not repeated. Okay, the isomorphism induces an isomorphism between the center of two algebras, and the center of the group algebra is a vector space with bases given by these conjugacy classes. So let's consider an element, I write it in a second, in the center of the group algebra. What's this element? How can we write this element? Well, you can write it, well, any element of the group algebra is, once we identified, say, delta functions with the elements of G, is of the form, well, a linear combination of the elements of G with the f of G is a function. This is just a coefficient in C. But to be in the center, an element, as we said in the previous slide, in the previous board, has to be a linear combination of the sums of the conjugacy classes. And for this to hold, you need f to be a class function. That is a function, is a term we have used several times, but repetita iuvant, that is a function which is constant over the conjugacy classes. Just to make an example with S3. So for instance, you consider these elements, okay? If we consider any, well, let's make more room here for the coefficients. If we make a linear combination of these elements with arbitrary coefficients, we obtain an arbitrary element of the group algebra. If we want an element in the center, we have to make sure that the coefficients we put in front of the elements is constant over the conjugacy classes. So for instance, we can put 3 here. There's no problem here, but because the conjugacy classes consists of one element. If we put I in front here, the coefficient, then we have to make sure that I is the same coefficients here. And if you put -1 here, then it has to be -1 also here, okay? In this way, we have that this is 3 times 1 plus I, sum of the conjugacy class, minus sum of the conjugacy class, okay? Good, so an element in the center of this will be of this form where f is a class function, a function that is constant on the conjugacy classes, okay? So that we can take the value of f out and we get the sum of the over a conjugacy class, which is a basis as a abelian group, as a Z module of the center. Now we go back to this isomorphism, but actually we consider a composition of two isomorphisms, because we have CG, which goes in this direct sum where chi ranges over the reducible character of G, of the endomorphism of this module. But we can fix a single, fix a particular k, chi, near G. Here I'm using chi both as a dumb variable, I mean a variable here, and a particular irreducible character. Okay, we consider the composition, and of course the composition of these two algebra morphisms. This is just a projection. And this is the isomorphism, the algebra isomorphism we already discussed several times. So the composition of these two is an algebra morphism. From CG to end V chi. Okay, so what's this? This is we have repeated this several times, but this is nothing else than the matrix algebra. Okay, so it's chi1 times chi1 matrices. Okay, because remember, chi1 is the trace of the identity matrix, and so it tells you the dimension. Okay, the dimension of V chi is the value of the character at 1. Okay, I mean once one gets used to characters, it tends to write everything in terms of character. So it's a dimension of a vector space, but it's also the value of the character, because we are talking of the trace of the unit matrix of size this dimension. Okay, this is an algebra morphism, epimorphism. Okay, so in particular, this is important, it's surjective, because this is an isomorphism, this is surjective. So we will have that this induces a homomorphism, a morphism, which is not an isomorphism anymore. I mean, this is also not an isomorphism anymore, because this is an isomorphism. These two have the same dimension. This is small, it's just one of the summand in this direct sum. So this induces a morphism from the center, okay, to the center of this. And what's this center is scalar matrices, okay? So what's the center of a matrix algebra is made of matrices lambda, 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 scalar matrices, not just diagonal, but a constant element of the diagonal. And when I haven't written anything, there are zeros, okay? Okay, how does this isomorphism work? We'll call it, let me think, well, phi, okay? Well, phi is very simple, because you can call it rho, because what does phi do to an element here? It simply applies rho. Remember, chi is the character of a representation rho. It simply applies rho to all elements of G. Okay, you recall that an isomorphism of algebra from here to here is given by the images of by prescribing the images of the elements of G, which are a basis of the group algebra. And how do you prescribe it? In this case, you apply a certain irreducible representation. Okay, so rho is the representation, is the irreducible representation. Which affords chi. Remember, afford is just a high-level word to say that whose character is chi. Okay, but I mean it's a standard terminology, so we'd better get used to that. Okay, now the point is, this is an element of the center, because this is a class function. So we have taken an element in the center. So this will be an element in the center of this. So this will be lambda times, this is a chi1 times chi1 identity matrix. Okay? How can we compute lambda? So let's copy this, and then we'll okay, there's something more. Add to new page. Great. We'll put it here. Okay. So, well, forget about this. So how do we compute lambda? Well, it's simply a matter of taking the trace. Okay, take the trace. So if you take the trace on the right, these are just coefficients. These are just element of C. So the trace on the right will simply be chi of G, because by definition, chi of G is the trace of rho of G, G, because rho is a representation affording chi. And on the right, what do we have? Well, this is lambda, 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 lambda. So the trace is the sum of all this. So it's lambda chi 1, okay? Remember that chi 1 is nothing else but the dimension of the vector space, and say the dimension of say of the side of a matrix here. Good. And yes, and so this gives us the formula, because lambda, this value is equals, let's write it like this. Well, let's put chi 1 here. But sorry, let me rewrite this, which is horrible. Now there is a way of rewriting this part here, because this you see, this is the sum over G of the product of two functions, and both are class functions, and then you can use the scalar product, okay, the inner product, the inner product of two functions. Well, they don't need to be class functions. In this case, they are. Is the sum of this is important, AG conjugate BG, okay? And I want to leave FG as it is. And of course, you can exchange the two terms, this commutative. So there's no 1 over G here. So let's write this here, okay? And now we have the scalar, the inner product between, okay, we'll put it like this, chi conjugate F, okay? Because when you apply this formula, there's a conjugate here. This is the usual conjugate. And if you conjugate again, you get a chi of G, okay? So the 1 over G has been inserted by taking an order of G here, and here you have this. There's a particular case that will be important later once we have developed these ideas of integrality. And as a particular case, so remember, this is a class function, okay, on G. And particularly useful class functions are characters. So what you can do, you take F to be chi conjugate, okay? So this is just the conjugate of the character. And then this formula, then the formula becomes lambda equal order this, okay? And since chi is an irreducible character, so it is conjugate, this equals this element, okay? And this will be important because we will prove later, using the theory of algebraic integers, that this is an integer. And this will imply, later, this will imply that the degree of a character divides the order of G. If you look back at the example we have taken, like, well, in the case of abelian groups, all irreducible characters of order 1, have the degree 1, so of course their order divides the order of the group, because 1 divides every natural number. But if you, for instance, in S3, we had irreducible characters of degree 1, 1, and 2, which are all divisor of the order 6 of S3. And when we had S4, for instance, we had 1, 1, 2, 3, 3 as the degrees of the irreducible characters. And of course, 2 and 3 divide 24, which is the order of S4. So later we will see that the fact that we obtain this lambda with the particular choice of f in this form, it will imply that the degree of a character divides the order of G. So this puts a restriction on the dimension, say, of the irreducible representations of a finite group. I mean, it has to divide the order, its character, yes, its degree has to divide the order of the group. Good. And now we can start with the integrality. So one way of doing with integrality, we will soon be discussing algebraic integers, which you will have probably seen elsewhere. But there is a slightly more general concept which says the following: let R be a commutative ring so an arbitrary commutative ring, not necessarily the complex number or the like, of characteristic 0. And so a commutative, it's, I have never mentioned it explicitly, but these are unital rings. There is ring with unity, okay? Hence, I can speak of a characteristic, because the characteristic, as you remember, is the additive order of the unity, which means in particular in this case that the unity has infinite period. Characteristic 0 means that. And this follows that R contains Z as a subring. Of course, it's not exactly that contains Z, but up to isomorphism. If we consider the subring as the subring, okay, as the smallest subring containing 1. Okay, so the prime subring, you consider the prime subring being of characteristic 0 means that this subring is isomorphic to the integers, and we'll just say that it contains the integers. Okay. One example will be, well, we'll have examples, for instance, in the group algebra, but I can say this later. Okay, so we have a proposition which states that for such a ring, so commutative and characteristic 0. So for instance, this does not apply to the group algebra, but it applies to its center, okay? Because the center of the group algebra is commutative, because it's the center, so the elements of the center commute with everything, and in particular among themselves, and of characteristic 0, because it's an algebra over the complex number, so characteristic 0. For such a ring R, well, no, it doesn't deserve red color. For such a ring R, and any alpha in R, any element of R, the following are equivalent. Three properties. Well, I could have given the definition of an integral element first, and then prove that the definition is equivalent to the other properties. We'll do it the other way around. So first we prove that three properties are equivalent, and then we'll define an element to be integral if it satisfies any of the three, okay? So the first one tells you that there is n greater at least 1, and the monic polynomial let's write it. X to the n plus a minus 1 x to the n minus 1 plus and so on plus f0. So an element, a polynomial, but note it's a monic. So the coefficients of the highest term is 1, of which alpha is a root. Which means, of course, that alpha to the n plus an minus 1 alpha n minus 1 plus that and so on plus alpha plus a naught is 0. Okay. The second property tells you that that the subring of R given by, well, we'll call it Z alpha, which is the familiar object. It consists of all the values in alpha of integer polynomials. Okay, so it's say it's a simple extension of Z with the element alpha in terms using the terms that we employed in the algebra course. Explicitly, this is given by all expressions of the form B naught, let me use letters different from B alpha plus the BK alpha K, where K is any natural number and the BI are integers. Okay, but this compact form is superior because it tells you you don't need to say for any K and for any BI. You simply say take any polynomial and evaluate all the polynomials and evaluated them in alpha. This is the value of the polynomial in alpha. Oh yes, what do I have to say about this? This subring is finitely generated as an abelian group, which is the same, sorry, as a Z module. What does it mean? That is, there is a certain integer, let me say, n and k are, well, k is a dumb variable. There is an integer t, a natural number, and gamma 1, gamma t in R, such that every element of R is a Z linear combination of the gamma I. Okay, so it's finitely generated means exactly this. Okay, it means that there is a finite number of elements in R such that every element of R can be written as a Z-linear combination of the gamma I. We'll finish this on the next slide, and so let's copy and finish it. No, sorry, I'll do it. Okay, I don't want to take unnecessary stuff, so add to new page. Good. Number 3, okay, tells you that the subring Z alpha. So 2 was telling you that if you consider the subset of R, the subring of R, Z alpha, then this is a finitely generated, okay? 3 is weaker, and it's very useful because it tells you that the subring Z alpha of R is contained in a finitely generated say, abelian group or Z submodule of R. So it's not that the ring subring itself is finitely generated, but it's simply contained in a submodule which is finitely generated. Actually, we will see that that by general properties, 3 implies 2 by general properties of finitely generated modules of Z. But okay, well, we'll see that in a second. Good. So let's prove that the 3 are equivalent. These 3 properties are equivalent. So first, I assume that alpha is a root of a monic polynomial with integer coefficients. No, sorry, I have to go to the next page. Okay, so 1 implies 2. This is the proof. So let's get back so we check what we have to prove. We have that alpha is a root of a monic polynomial with integer coefficients, and we have to prove that this ring is finitely generated as an abelian group. But this is relatively easy because a claim Z alpha is generated as a Z module by the powers 1 alpha n minus 1 of alpha. Well, recall alpha by assumption 1 is a root of a polynomial, a monic polynomial of degree n. This is well, an argument that no doubt you know well, but let's review it. So we'll take f alpha, an element of Z alpha, okay, for some polynomial fx in Zx, or f in Zx, okay? And let alpha by assumption 1 be a root of the polynomial we will call simply a, which is x to the n plus an minus 1, xn minus 1, plus a1 x plus a naught, okay? Now, this is a monic polynomial. We know that zdx, no, this deserves a red underline. Zx is not a Euclidean domain in general, but I mean, you cannot divide any polynomial by any, I mean, two arbitrary polynomials, one from the others, even if they are different from 0. But since A is monic, you can divide f by A. And what do you get? You get f equal a times q plus r, where either r is 0, okay, or the degree of r is less than n, which is the degree of a. A being monic has evidently degree n, okay? Now, if you evaluate this in alpha, what do you get? You get at f alpha, which was our arbitrary element of Z alpha, is A of alpha, Q of alpha, plus R of alpha. But alpha is a root of the polynomial A, so this is 0, okay? So this means that what we get is R alpha. And you see, this is either 0 or has degree less than n, which means that this will be something of this form. Let's write not, I'll write it better. Times 1, this is useless, but and so on. So the degree is less than n, or the polynomial might be 0. And you see what we have here. We have here that every element of Z alpha is a linear combination of with integer coefficients, okay? Because This polynomial, of course, is an integer polynomial, so Q and R are in ZX. So we have found that F alpha is a linear combination with integer coefficients of 1, alpha, alpha n minus 1. That's right. So F alpha is a Z linear combination of 1, alpha, alpha n minus 1, as claimed, okay? Just a matter of polynomials. Okay, and that's the 1 implies 2. Now we have to prove that just a second. Okay, yeah, the converse. The 2 implies 1. Okay. So 2 tells you that we know by assumption that Z alpha is by assumption. So recall, this is just the set of values of all the integer polynomials on alpha, is by assumption a finitely generated Z module. Okay. Now there is a lemma in the notes that you have probably seen in courses like commutative algebra that you should have taken, but otherwise you can see it in my notes, that tells you that Z alpha is a finitely generated module over a Noetherian ring, the Noetherian ring Z, the result tells you, the result I'm going to quote is that if I have a finitely generated module over an Noetherian ring, it doesn't matter whether it's Z or something else, then Z alpha is Noetherian. Is an Noetherian module. The proof is not difficult. I mean, it's well, it's in the notes. Okay, it's lemma 1.11.3, but I'm pretty sure you have seen it in other courses like commutative algebra, as I said. So this is a Noetherian module, but then you see one can consider the ascending chain, well, chain of Z submodules of Z alpha generated by first 1, so the multiples of 1, then 1 alpha, 1 alpha, alpha squared, and so on. 1 alpha, alpha to the k. Okay? So you consider the first submodule with say M1, M0, M1, M2, and so on, Mk. Okay? So the M0 is generated as a Z submodule by 1, so the multiples of 1. M1 is generated by 1 and alpha, so linear combination with integer coefficients of 1 and alpha, and so on, 1 alpha and so squared. Now, this is an Noetherian module, so this ascending chain has to stop. Okay, so there is an integer, there is an n, okay, n, such that the sequence stops. So mn minus 1 equal mn equal all what follows. Okay. But now you know that the notation for this submodule is chosen so that alpha k is in mk. So alpha n is in mn, but by the fact that this is an Noetherian module, this equals mn minus 1. Mn minus 1 is the set of linear combinations of 1 up to alpha n minus 1. So this means, okay, so there are integers ai such that alpha to the n is a linear combination with these coefficients of the elements 1 alpha n minus 1. So a naught, this will be a naught times 1. But you see what we have here, well, there's a matter of signs, but, and this shows is the root of the monic polynomial x to the n minus in minus 1, xn minus 1 minus and so on, okay, which is 1, okay? So the fact, so here we have used the fact that a finitely degenerated module over a Noetherian ring is a Noetherian module. So we have taken this ascending chain of submodules generated by, I mean, linear combinations of, and when it stops, you get this polynomial. And we are left with the last step, which is the, well, yes. Let's get back a second to the statement. Of course, 2 implies 3, because 2 tells you that this subring is finitely generated, and this tells you that this subring is contained in a finitely generated submodule. So if the Z alpha is finitely generated, then you can simply take Z alpha as this subring, as this finitely generated submodule, okay? 2 implies 3 is obvious. Z alpha itself is a finitely generated Z module. And 3 implies 2 is, well, disappointing, because I'm going to quote something. And this follows from a general fact. Though we will have then a proof of a similar statement in a different context. This follows from a general fact that if M is a finitely generated module over Z, so finitely generated means that all elements are in a combination of a fixed finite number of elements. In general, more generally, you can take it over a PID, principal idea domain, for instance, a Euclidean ring. Then every submodule is finitely generated, of M is finitely generated. And there is a proof also in the notes in section, see section 113. And you should have seen this result. If necessary, I can go over it, or I might even discuss it if I have time. So the proof that 3 implies 2, let me just review it in a second. It tells you if Z alpha is contained in a finitely generated Z submodule of R, you simply use the fact that a finitely generated, the submodules of every finitely generated submodules of Z, in general of a PID, are finitely generated. So 3 holds, because 3 tells you that this is finitely generated as an abelian group, that is as a Z module. So 2 implies 3 is trivial, and 3 implies 2 because as this finite generated sum modulo takes that alpha itself, and the converse that follows from this general result. Okay. And the point is, but I'll resume tomorrow, that any element alpha that satisfies one of the 3 equivalent conditions is called integral, an integral element. Okay, but we'll give these proper definitions tomorrow. That's all for today. Thank you for listening.